Okay, so we have the softmax function. It's great. What we're going to do now is look at an example of the MNIST data set, right? Remember, the MNIST data set, I believe, was a collection of, handwritten digits, each of which has how many pixels? It's a 28 by 28 pixel grid, where you have like, this is your pixel grid, this is your number, handwritten digit, right? And then this one, like there are 28 pixels in this way, and then 28 pixels this way. And then 28 times 28 is equal to 784. So in total, you have 784 input features, right? And each of these are a pixel brightness, right? So you have 784 inputs. And what we can do is, instead of like representing it as a 2 by 2, a two-dimensional grid, we can represent it as just a stack, right? Where we take everything that's in the first column, then everything everything that's in the first row, then second row, then third row. We just unwrap it and put it into a very long chain. And so this has maybe some dots, and then the last one. And then this is 784 long. So we'll just pretend 784. Um, and then let's say, since we're using neural networks, what we'll do is we will have four in the second layer. Four, this is our first hidden layer number one. So this is the input layer, hidden layer number one. We get to choose how big this is, but I'm going to choose four. And then let's say there's maybe four more over here, hidden layer number two. And then the output, which is 1, 2, 3, all the way to 10. These are 10 outputs. And basically the first one would correspond to, is it of the first class or not? Is it of the second class or not? Is it of the third class or not? And so on to, is it of the 10th class or not? Right? Where the reason that there's 10 outputs is because the number that's actually handwritten in the image can take on the value 0, 1, 2, 3, 4, all the way to 9. And so here we've arbitrarily chosen only two hidden layers, and each of them have only four hidden units in each of them. And let's say each of these, is a logistic regression problem, right? We're using these for logistic regression. This is a logistic regression um, computation that's happening here. And then same thing for all of these four. And then for this, let's say, this is a logistic regression computation of all of these. And same thing for everything here. And then out of these, this is logistic regression we could do again. Or we could just do linear regression on all of them. And then, so let's say this is linear regression. So this one is the only one that's linear. And the output, what we're going to do to the output is apply softmax. Softmax onto the linear output. Okay. And that could be a strategy for finding out what a handwritten digit is. Now I want to talk to you a little bit about the sigmoid function. So remember, the sigmoid function takes in a value x, and it outputs just this simple function, which is 1 over 1 plus e to the power of negative x, right? And remember, it looks kind of like this. I want to consider what would happen if we didn't have the sigmoid function applied to the output of the linear layer that happens here. So remember, what happens is that we first combine them as if it was linear regression, and then we apply the softmax function, not the softmax function, the logistic function, in order to get the associated probability, in order to get the classification type, right? And so what we call that is an activation function. So in this scenario, the sigmoid function is our choice for the activation function. activation function. And activation functions are actually the key to neural networks. And I sort of glossed over why we use logistic regression before, but now I want to talk to you about why do we do that rather than just using linear regression all of the time. So let's say we have a simpler problem, which is two inputs, two intermediate nodes in the first hidden layer, and then an output. Okay. And so I'll do a little bit of math with you. This is x1, let's say, and this is x2. And then let's say that this right here, we combine these using W1 and W2, and we combine these two using W3 and W4. Okay. And let's say we combine these two with we can use W5 and W6. Okay. And so what's going to happen here is, and then there's a B, let's say this corresponds to B1. There's a B1 that's there. There's a B2 here, and there's a B3 there. And so how would we get this node? The value of this node would be given by W1 x1 plus W2 x2 plus B1. Okay. And this is if we're not using logistic regression. And I want to show you why why the sigmoid function, applying the activation function, the sigmoid function is so crucial here. So here you have W1 x1 plus W2 x2 plus B1. And then to compute this node over here, you have W3 x1 plus W4 x2 plus B2. And then this is, let's say, H1, and then this is H2, let's say. How do you combine those to get this node? So to get this node, what you would do is W5 H1 plus W6 H2 plus B3. And that's that, let's say, is our output, which is Y. Now we actually have an expression for H1 that we can substitute in here. So let's do that math. So Y is equal to W5 times, in parentheses, W1 x1 plus W2 x2 plus B1, and then plus W6 times whatever the expression is for H2. I'll just copy that in, W3 x1 plus W4 x2 plus B2, and then at the end plus B3. Okay, so let's expand this and sort of reduce this down. I'm going to factor out x1 and find out all of the common factors. So there's W5, W1 plus W6, W3 plus x2 times, what is the factor for x2? W5, W2 plus W6, W4. Okay. And then plus, oh yeah, we have some constants here. I'll continue on the next line. We have some constants here, W5, B1 plus W6, B2 plus the B3 that's at the end. And we'll put that in parentheses. So plus all of this. I want to point out to you that this right here, let's say we said that this is capital W1, and then we took all of this, made this capital W2, and made all of this into capital B. Now, that reduces down to y equals W1 x1 plus W2 x2 plus capital B. So we could have actually just redefined the value for W, redefined the value for W2, and redefined the value for B, and we would have gotten the same result as if we had done it for one layer. So it collapses down. And this is really like bad because we're introducing all of this extra complexity without actually achieving any extra complexity, right? And we're just making it more complicated, hand waving it, and we're not actually adding any value to our model. And I just wanted to point that out because because that is exactly the thing that the activation function is used to rectify. So let's consider if we had put, maybe I can switch colors for once. So if we had put sigmoid function around this, which essentially equates to making this a logistic regression node, and put a sigmoid function around this, and then yeah, so that was our new equation for y. Well, consider what would happen now. You can try and expand it out and try to reduce it down. But the thing is, you can't. You can't get it into this form like it was before. And that's because of this property of the sigmoid function. Sigmoid function has non-linearity. Because it has this property of non-linearity in its function. This is the function, right? In this function, when you draw it out, this function is what we call non-linear. And since it's non-linear, or I guess if you think about it, it's not really a line. And because of that, it cannot be reduced down to like linear stuff, right? All of this from before, if you ignore the red, all of this from before could be reduced down to this linear form, right? And this being a linear combination of x and 2, I guess, x1 and x2. But I guess like since sigmoid has non-linearity, it introduces this complexity that can't be reduced down, and it introduces something new, I guess. And so it's really hard to visualize how this works exactly, but I just wanted to let you know that that's why we have these activation functions. And why am I talking about activation functions and not sigmoid specifically? Is because there's more activation functions than just sigmoid. Here's a list of activation functions. There is sigmoid, like we just talked about, which looks like this. Based on an input x, this is your f of x. There is also this thing called ReLU. I think this is probably the most commonly used one. It's basically equal to 0 up to here. So this is the function right here. It's 0, and then it is this like y equals x over here. So basically the rule for this is that if x is greater than or equal to 0, then just set it to x, right? And this is the line y equals x, right? And otherwise, just set it to 0. So if x is negative in the negative portion, then just set it to 0, right? And over here, it just gets mapped to the same value that came in, okay? And this is also nonlinear. There's a nonlinearity there. There's also tanh, which is basically just sigmoid that's kind of shifted around. So this is what tanh looks like, right? And tanh is literally just sigmoid, but it's kind of stretched and moved around. And I guess there are other variants like silu, or like and I think CILU looks, which is a variant of ReLU. It looks something I think like this. And then there's like leaky ReLU, which looks like this. So instead of being exactly 0, leaky ReLU makes it like some kind of line that slope is not equal to 1. So on this side of the line, the slope is equal to 1, and on this side of the line, slope is equal to, let's say, like 0.1 or something like that. And it's shown to have, like, I guess, good results or whatever. But the whole point of this being that there are different activation functions, and when you're creating a neural network, what you would do is you would have the inputs, and each of these intermediate nodes, the way to compute them would be to use a linear regression model to combine them all, the W1, X1 thing. So if this is X1, there's W1, X1, W2, X2, W3, X3, and so on. You add them all together, plus the B at the end. And then on that result, you perform an activation function. So it's basically linear regression, and then pass that through an activation function. And then whatever these outputs are, you again feed them in as a linear regression. And then activation. And then again and again and again until you reach your final oh, sorry. I think I turned on the eraser. Let me switch back to pen. Until you reach your final output, and let's say you combine these 3 values, and let's say your task is to do a binary classification. So this is only one output and it's a binary classification. Then for the purposes of interpreting that output, you can apply the sigmoid function. Or if you have multiple outputs and they're a classification problem, then you can apply a softmax to go and be able to interpret your results. So you can, if there are multiple of them and it's a classification problem, then you could do softmax, or you could do just if there's only one of them and you have a classification problem, just a binary classification, whether one or the other, then you could do the sigmoid function, or you could just do nothing. And technically, you would be okay. You would be like okay to go for your neural network. It's just like it would be hard to interpret your results. So I'm just saying that in the output, it's kind of optional whether or not you want to include an activation function. That's more for your results interpretability. But in the intermediate layers, it's crucial because that is what adds the added complexity. It's not that you do the function again and again, linear regression and then linear regression and linear regression. That can be actually collapsed down into one linear regression. But if you do a linear regression activation, these activations, they serve as a wall between the linear regressions that don't allow for them to all be collapsed into a simpler function. That's what adds the complexity to your neural network. So thank you for listening.